Significance. We have seen that probabilities can be used to determine whether values are significantly high or significantly low. Previously, we referred to X successes among N trials, but we can adapt those criteria to apply to continuous variables as follows. Significantly high. The value X is significantly high if the probability of X or greater is less than or equal to 0.05. Significantly low, the value X is significantly low if P of X or less is less than or equal to 0.05. Now, the value of 0.05 is not absolutely rigid, and other values such as 0.01 could be used instead. Okay, now example 4, significantly low births using table A-2. Use the following criteria to identify significantly low birth weight grams of males. Assume that males have normally distributed birth weights with a mean of 3,272.8 grams and a standard deviation of 660.2 grams. Now recall that the value of X is significantly low if the probability of X or less is less than or equal to 0.05. Therefore, we identify the X values separating the lowest 5% of male birth weights. So we're going to draw a normal curve shading the desired area of 5%, which is equal to 0.0500. So we're going to draw our normal curve. Okay, we also know that the mean is given, and the mean is given to be 3,272.8 grams. Okay, and then we're looking at 5%, and so for the significantly low, so that means we're going to shade 5% on this left side. So we're going to look for a value of X that's going to be here. So let's shade that area. Because that represents, again, the significantly low amount. So that represents our 5%, which is equal to 0.0500. Okay, now keep in mind that we know that we also have our z-scale, where the mean is 0. So this is going to represent X, which is in grams. And this is our z-scale. And we want to find the z-score first that's associated with the area of 0.05. So we labeled our graph, we put our mean there, we shade the area to the left of 0.05, and then again we're looking for the value of X. Now, when using the formula of X, which is equal to the mean plus z times the standard deviation, we want to determine the z-score. So table A2, we must work with cumulative areas to the left for the value of X. The cumulative area from the left is 0.05. So if we search for that on our graph here, we're going to see that these two areas have 0.05 in between them. So what we do is we take a look at the average of those two z-scores. So what we're going to do is now take the average of negative 1.64 plus negative 1.65 and divide that by 2, and that gives us negative 1.645. And therefore this is what we get as our z-score, which again is the area that's in between those two values. So that means over here we get negative 1.645. Now keep in mind that z-scores can be negative. So now that we know what the z-score is, which is negative 1.645, we know that the mean is 3,272.8 and the standard deviation is 660.2. So the result of X can be found by using the formula version. So we have 3,000, or X is equal to the mean plus z times the standard deviation. So 3,272.8 plus negative 1.645 times 660.2. We multiply those together and then add to that number. We get 2,186.8. So therefore, x is going to represent 2,186.8, which is lower than the mean. So we see that the value of 2,186.8 grams is reasonable because it is less than the mean of 3,272.28 grams. So actually, that should be 3,272.8 grams. So the interpretation will be the following. The birth weight of 2,186.8 grams is on the borderline that separates significantly low male birth weights from male birth weights that are not significantly low.